We're Team EvolVerilog, Jared Kirschner,
Matt Belland,
and Shane Moon is also on our team.
So our vision was to evolve a hardware solution to a system with the idea that is it possible to design a system without any knowledge of its inner workings? To do this, we use a genetic algorithm where you have an organism and you evaluate how fit an organism is compared to the rest of the population, and then based on that, you determine how likely it is to carry its genetic material forward. However, because we're trying to evolve hardware, there are interesting questions around, well, how do you represent the genetic code of a hardware system?
And so originally, the way we represent the hardware is through a series of layers, each containing logical gates. And so we've got a fixed number of layers, fixed number of gates each, and in doing so it's easy to inherit from two different pairs. We can just take these two different layers, swap them out with each other, and it's an easy way of getting representation going early. But there were some problems early on with this decision in that if you've got one gate here that's being referenced by a series of gates further down, it can, by changing it, you can entirely change all of the outputs. And this is pretty bad when you're trying to keep good traits if a single change can mess up everything. And so we moved on to a tree representation where each output is isolated, and it's got a more interesting way of crossing over here. You just take a single node of a gate from one parent to another. You can swap those out, so you get all sorts of evolution inheritance behaviors.
So in general, the way our system organized is that we carry out the evolution in Python. We have an organism manager that manages the population of organisms. Each generation will take the list of organisms, convert them to Verilog files, run a hardware simulation on them using Icarus Verilog, parsing the results, and then passing that into a fitness function to evaluate how fit a particular organism is, and then carrying out the evolution with that information.
Cool. So we can run some quick demos here. The first one's just a basic Boolean equation here, where we're trying to output ones no matter what the inputs are. So if we run the process right here, we can see the fitness.
So what you'll see pop up is a cumulative distribution function that should generally move over to the right as the fitness improves. Here we're looking for a final fitness of 12. So we have a penalty for how large a solution is. So if it has too many gates, we'll consider it not good enough. And in general, the vertical separations are how many outputs it has correct. So we evolved the solution after 35 generations. Let's take a look at the representation. So this is the root of the organism, and these are its 3 different outputs. So we'll look at the different ways that it's outputting one. So here it's NANDing something with itself, which will always produce a 0, and then XORing it with itself. And because those will always be...
They'll always be opposite.
It'll always output a 1. Right. This one's a little simpler to understand. It's NAND of something with the not of itself, which will always output 1. This one's a bit more complicated, and you can see that it can actually evolve some really complicated solutions to do simple things. It's just a chain of NAND gates that ends up outputting 1 always.
Different every time. And so our other task here, we wanted to find a test that had a fitness function that was a little bit more fluid. And so we have a scootbot here, whose goal is to pick up as much food on this grid as possible with a fixed number of steps. And so it can start here, and it sees the world around it as inputs. It sees the 4 neighboring squares, and as outputs, it says whether or not it wants to move in each of those directions. We take it through a fixed number of steps, we see how well it does, we evolve better and better organisms. And some good behaviors generally, the traits that can be handed down are traits that keep the scootbot from being locked down in a position where it gets stuck. It's not able to move in any direction. Where it's for example, trying to move in opposite directions and doesn't move. If we come up with traits that don't let that happen, they lock that out, those get inherited more frequently. So we can run a test on this. as well, and the fitness is going to be out of 50.
So in this case, 50 it has 100 steps in a 10 by 10 grid in order to try to get all the 50 pieces of food. The fitness is how many pieces of food a particular organism is currently able to get based on its implementation. So right now, the best is actually 10 out of 50, which isn't very good. The result of a genetic algorithm is different depending on the set of initial organisms in the population.
Would you like to demonstrate that as well? I think this guy's probably getting...
So we'll actually, to demonstrate that it'll be different depending on what we put into the system initially, we'll rerun it.
The seed genetic material is very important.
So you'll see that this one's already doing a bit better. The idea is you want different organisms to evolve good traits and then have them, if one organism has one good trait and another has another good trait, you want them to swap so that you end up with an organism with two better traits. In this case, to a random grid, we're currently able to get 43 out of 50 pieces of food just with a combination of simple genetic logical rules.
Cool. So, we're reaching the end, but yeah.
Yeah. But so as you saw, it can successfully do some problems, but other problems don't work. The layers representation doesn't work very well because the traits are horizontal when really we want them to be vertical. Each output is dependent on all these traits, so if you change one, it changes all of it, which is really bad. So we try to change that with the tree representation. So each output has its own tree, and if it gets an output correct, it can pass that trait on to its children without affecting all the other ones. The problem with this, however, is that the output is always 0 or 1. So if it either gets it completely correct or it gets it completely wrong, and there's no way of telling if it got closer or farther away compared to another one. So you can't tell if it has good traits but still got it wrong, or if it has completely bad traits. So therefore, none of the good traits go on, and the trees are therefore generated randomly. So anything with a small number of outputs doesn't work very well. Anything with a large number of outputs of simple gates, such as all ones or a scoop bot, works really well. Next step is to make an automated test bed, or perhaps try a different representation that would be able to evolve for a single output.
Sweet guys, thanks.